Alright, in the last video for this midterm, beta oxidation. So beta oxidation is a three-step process of activation, transportation, and oxidation. Prior to this, the fatty acid has come into the muscle cell, more than likely is the location that we burn our energy to use our energy, from lipoprotein lipase cleaving the fatty acid from the triglycerides in storage, be it adipocytic storage or muscular or liver. Alright, so beta oxidation. The first step we see in the cytoplasm of the cell, and it's the fatty acid plus the CoA molecule attached to the sulfhydryl group. And this is completed through acyl synthetase, excuse me, and it burns two phosphate groups actually in doing so. So we activate using ATP and it forms acyl CoA, fatty acyl CoA. We then use L-carnitine to come in and oxidize this or reduce. I can't remember exactly which redox way this is going chemistry wise, but they get what's the word I'm looking for? Catalyzed by the CAT1 or CPT1 translocase right here, or transferase, excuse me. And this is actually the rate limiting step for beta oxidation. And the only known, I believe, the only known inhibitor is actually malonyl-CoA. And this is not directly understood, I don't believe, at the moment, but it's known that malonyl-CoA is part of the fatty acid synthesis rotation. So if we're laying down fatty acids, then we don't want to be burning fatty acids. So a lot of malonyl-CoA will be in circulation, inhibiting the beta oxidation when we want to synthesize fatty acid storage. So we use acyl CoA plus L-carnitine through the use of CAT1. We pull the CoA molecule back off, and it stays in the cytoplasm. And we form acyl carnitine, which then crosses over the outer mitochondrial membrane, and it actually goes all the way through and over to, oh, my flash turned off, sorry about that. It goes all the way over to acyl carnitine translocase, which is still part of the second function of beta oxidation, which is transport. So we go into the inner mitochondrial membrane, which is where all of our powerhouse stuff happens. We have our acyl carnitine that we formed up here with CAT1, pulled all the way through the membrane. We join it back with a CoA molecule using CAT2, which I actually, whoops, I should have drawn that. This catalyzes this. It gives us the L-carnitine molecule. Jeez. L-carnitine molecule and acyl CoA again that we had up top before we started the transport process. And this is actually where beta oxidation really starts coming into play. And you'll notice I also have the electron transport chain here, as this is where we oxidize everything fully from here. It's conveniently located. So we have an acyl CoA molecule that we now join with an H2O molecule for every turn. Every round of beta oxidation joins an H2O molecule and a CoA molecule. And we retrieve an NADH and an FADH from each cleavage. So what we get is an acetyl-CoA, which then leaves to go to the Krebs cycle and give us our ATP yield from that. And we also have these NADH and FADH2 molecules, which go to the electron transport chain and yield different amounts of energy based on where they enter the chain. So we have an acetyl-CoA and an acyl-CoA. The acetyl-CoA leaves, acyl stays behind for another round of beta oxidation. It should be noted that this acyl-CoA is going to be the same as that one, just minus 2 carbons, which we see, which left in the acetyl group. So the acyl-CoA will then keep going through all of these rounds. So let's say it's a 16 carbon fatty acid chain, acyl-CoA. So we'd have 8 total acetyl-CoAs, as well as 8 NADH and 8 FADH2 energy yield. Those go straight to ETC, as I mentioned, and the 8 acetyl-CoAs will go towards Krebs and give us our energy that way. And this is the overview of fatty acid beta oxidation.